Hi, my name is Changyuan Zhang. I'd like to talk about my thesis project in this video. This video is mainly focused on the 3D structuralized scanner and the 3D data. This video will firstly discuss the current status of the 3D data in background section. Secondly, the video will discuss the three kinds of 3D scanners and find out why is the structuralized scanner is the equipment that most suitable for 3D data collection. For next, I will introduce the 4 experiments conducted in the project. Also the results. Finally, I studied some 3D datasets and their application with CNN to understand the application difference of 3D data and its efficient utilization. Okay, let's start. 2D Facebook recognition was first learned in 2010 when Facebook's face verification feature went online. The technique is complete by both 2D image and CNN. A crucial part of this is the 2D image dataset. So far, there are more than 360 large datasets, including MISP and WOC, which provides a solid data foundation for 2D image recognition. 2D data has fatal drawbacks. Take face recognition as an example. When a camera captures two similar faces, it is likely to identify them as the same person, or when the camera captures different angle of a face, it might identify that person as someone else. 3D data comes into researchers' vision. 3D data provides 3D raw data, texture mapping, and point cloud data, which enables researchers to add more marker points on 3D space and makes the recognition function more rigorous. At present, there is only 18 3D public datasets, such as Kitty and ShapeNet, have limited the progress of 3D data learning to some content. Therefore, making more datasets is the most urgent need in the 3D data field. So what equipment should we use to collect 3D data? Currently, there are 3 types of scanners that collect 3D data: coordinate measuring machine, structuralized scanner, and laser scanner. The CMM works by using mental balls probe to touch every point on the object surface and then create a point cloud data. Then use structure light or laser sensor on CMM to get a 2D material map of the object. Finally, 3D reconstruction is carried out by the software. Ordinary CMM has no structuralized sensor or laser sensor, since CMM is generally only used for industry measurement. Ordinary CMM has only generates point cloud data. With a structuralized or laser sensor, CMM can get colored 3D raw data. The accuracy of point cloud data obtained by CMM is very high, reaching the level of nanoscale. It also has an obvious disadvantage of being extremely slow scanning speed. The structuralized scanner uses triangulation method to measure the distance between objects and the projector as the light source. It projects a light pattern consisting of black lines and white lines to the objects. When the light pattern arrives at the surface of the object, bulge or depression of the surface of the object will cause the light pattern deformation. The deformation data will be transmitted to the camera to determine the physical structure of the object. Finally, 3D reconstruction is generated through the software. Structuralized scanner accuracy is also very high, depending on the size of the object. The accuracy range is 0.1 to 0.01 mm. Its depth of field range is from 300 mm to 500 mm, which means the structuralized scanner can work remotely. Its scanning speed is also very fast, usually 2 to 10 seconds to complete a scan. The disadvantage of structuralized scanners is that they are very sensitive to the light conditions in the scanning environment. If the light is unstable, the scanning result will produce a lot of noise. In addition, the material of the surface can have a negative impact on the scanning results. Laser scanner and structuralized scanner are basically the same. They use triangulation method to calibrate the position of the object. The only difference is that The laser scanner using laser emitter as a light source, not a projector. Among of the three scanners, it has the lowest accuracy range, but can reach as high as 0.01 mm, and its depth of field is about 100 mm, which means it can only perform close-up scans. Its scanning speed is also relatively slow, with each scan exceeding 10 seconds. In addition, it can scan for either transparent objects or highly reflective and soft objects. In conclusion, among the three kinds of scanner, the CMM has the highest scanning accuracy, but the lowest scanning efficiency, and can only obtain the point cloud data when the structured light or laser sensor is not applicable. It is clearly not appropriate to use CMM to collect data without regarding to industry measurements. The laser scanner has a relatively low depth of field, which is only suitable for scanning large objects parts one by one, and then stitching them together. Certain data loss will occur during the staging process, and it cannot scan non-grid objects, such as sponges. Structured light scanner is the most suitable equipment for 3D data collection. Its accuracy is higher than laser scanner and scanning efficiency is higher than CMM. Most importantly, its defects can be solved manually by researchers. Next, let's move to the experiments. 4 experiments were carried out in this project, which were divided into Phase 1 and Phase 2. The main purpose of Phase 1 was to get familiar with the operating of structured light scanner and the solution for its defects. Phase 2 will generate a 3D dataset through Phase 1's experimental experience. The experiment in the first step is to learn the basic setup of the structured light and focus on the impact of binocular and the monocular cameras on the scanning results. Secondly, the impact of the camera placement angle on the scanning result. Since HP has published the detailed scanner operation and installation methods on the project in the introduction page, this experiment overlooks the learning process of HP 3D scan in the early stage of the experiment. Before the experiments, the hypothesis is that at the same camera angle, binocular camera has a higher scanning quality than monocular camera. The experiment results shows that the monocular camera was the least quality when its angle was 15 degrees, and its vertex spacing was only 0.268 mm. The accuracy of the other 3 scanning methods does not differ much, among which the effect is the best. And the scanning result with the lowest noise point is the binocular camera, and the angle was 22 degrees. Compared with binocular camera, monocular camera has a large number of noise points, and even caused object structure deformation. You can have a look on the dark hand. The second step, the experiment was carried out in 3 environment light. Under natural light, the first scanning time is 9 AM. Because there is enough sunlight outside, it is more likely to leak the impact of highlighted sunlight on the scanning results. The second scan took place at 15 PM, when daylight was relatively dark, and the results were compared to the first scan to see the differences in the effect of bright and low light sunlight on the results. The last scanning time was between 12 and 1 PM. The reason for choosing this time period is that the outdoor light varies greatly, turns bright to dark, between 12 PM and 1 PM, which can better reflect the impact of natural light of high and low brightness on the scanning results. The experiment also set up interior light and darkroom scanning. The light source of darkroom scan is only light from the LCD projector, and the scanning platform is covered with black coat. The experiment will eventually compare the effects of the 3 ambient lights on the scan to explore which ambient light generates the best scan results. All experiments were carried out indoors. The results shows that the darkroom is the most suitable environment for structured light scanning. The scanning results are closer to the original color of the object, and the scanning results have almost no noise and no physical deformation. Natural light. The scan was the worst, with morning and evening scans showing exposure points and color distortions. Results from interior light are similar to those from dark rooms, but they have degree of color distortion and a large number of noise. The third step of the experiment starts from the defects of 3D structured light scanner. Firstly, scanning black objects, whether smooth or matte, may cause the scanning results to lose some of the image data. Secondly, matte surface objects can also cause the image data loss or noise increase. Thirdly, high reflectivity of the object surface will lead to the scanner camera overexposure, resulting in color difference. The last, light scatter happens when it hits transparent object, preventing the image from reaching the scanner's camera. Therefore, this experiment explores the defects and the solution of structured light scanner by scanning two black, including the matte and smooth surface objects, one with transparent surface, one with non-black matte surface, and one with smooth surface and high reflectivity. All experiments were carried out in dark room. Experiment results shows that when scanning an object with a transparent surface, structured light scanner will be unable to image because of light passing through the transparent surface. The black object, whether the matte surface or smooth surface, will absorb some light, and the information cannot be transmitted to the camera, resulting in the missing part of the scanning image. For objects with a high reflectivity and smooth surface, the light from FCD projector will scatter when it reaches the surface, which means that when the light reaches the surface, it may reflect in the other direction rather than back to the camera, resulting in part of image not appearing in the scanning result. When light strikes the scan object with a matte surface, not only does it scatter, but it can also diffuse, causing light to bounce back and forth in random direction as it passes through the surface. This means that light may be refracted on another surface of object and sent back to the camera, resulting in a double image. CMM is often used to scan workpieces with scars that are not easily visible to the naked eye. If scars of the workpieces is relatively smaller than the CMM detector head, then patient inspection material sprays are used to simulate the scar. The principle is that the spray forms a thin matte coating on the surface of the object, which reduces the reflectivity of the object. Therefore, after the end of this experiment, I have used the dye-penetrant inspection material spray on the surface of scanning objects to explore whether it can solve the defects of structured light scanners. Finally, all the scanned objects except the object with transparent surface materials were successfully used by the scanner to generate a high-quality image. Phase 2. Data Collection Experiment. The dataset contains 10 main classes. Each class has 10 objects. And the dataset has 100 OBJ 3D fields, 100 MTL 3D material library fields, 100 XYZ 3D point cloud fields, 100 PNG 2D colored mapping fields. Here is some sample from the dataset. The largest amount of dataset is the dataset for automatic driving. This part of dataset is mostly combined with the laser scanner and the GPS technology to obtain the 3D point cloud and the colored image and record the position information of the object at the same time. The least amount of dataset is applied to the face or body recognition, and there are relatively few researchers in this field. This may be due to the motion sensing camera's temporary inability to obtain high-quality data, and it can only scan object to point cloud data. For face scanning, researchers prefer to use structured light scanners and laser scanners because they are more accurate and depict face in great details. The dataset of indoor environment is also complete by structured light scanner. The difference is that the information of multiple objects in the room needs to be scanned. The researchers add a GPS radar component to the scanner to record the position information of all objects in the space. 3D object datasets are generally used for object recognition in academic research, and the number of datasets is very small, which is mainly collected by a structuralized scanner, because its scanning speed is fast and scanning accuracy can meet the needs of the research. Most importantly, all the 3D object datasets that have been published included 2D RGB images, 3D original fields, and point cloud fields, which means that 3D object dataset can meet the requirements of various applications, because the other three application directions mentioned above all require OBJ original data and point cloud fields. To sum up, the use of structuralized scanner can produce the best quality 3D dataset without considering multi-object scanning of detection. Point cloud fields are most important, regardless of where the 3D dataset is applied. Point cloud information usually need to cooperate with CNN to realize object recognition and prediction or 3D reconstruction. However, CNN also has some disadvantages. For example, when researchers want to use CNN to convert point cloud fields into voxel image information, some part of geometric structure is often missing, resulting in the decrease of accuracy. This is because the spatial location of each point in the point cloud data is unordered. Scholars have proposed many new types of CNN to solve the problem. For example, SCN and KCNet have achieved more than 90% accuracy in the shape classification based on the point cloud. In 2019, Changyuan Zhang proposed the RSCNN, that is, relationship CNN. Its core logic is to determine the position relationship between every 2 points in the point cloud, and makes the point cloud data form a virtual rigid surface before the 3D reconstruction. At present, RSCN has the highest accuracy in object shape classification.